Okay, so, once more, take this jar out of the microwave at 11:10. 2 minutes later, read the temperature, it's 140 Fahrenheit. 11:15, it's down to 115 Fahrenheit. Your room temperature is 70 Fahrenheit, and we're going to assume Newton's law of cooling. Ask what was the temperature at 11:10. When will the temperature be 100? Okay? Because when the temperature is 100, we dump this in with something else and put it in the oven, so it starts out at just the right temperature in the oven, so the recipe works, and you're not eating undercooked or overcooked food. Okay. To model this, okay, let T be the time since this was taken from the microwave. And we can interpret this. According to Newton's law of cooling, the rate at which the temperature changes is going to be proportional to how far the temperature is from 70. Okay? So it's the relative temperature, the temperature relative to the room. So I'm going to say relative temperature is 70 degrees at T equals 2. And then .70 degrees is 140 degrees minus the room temperature, which is 70. Okay, the relative temperature is what? 115 Fahrenheit is 115 minus 70 relative. That's 45 degrees at T equals 5. We've got to subtract the temperature of the room from the temperature of the jar that's cooling. So temperature and I'll write REL down here for relative temperature. It's T0 relative, in other words, your original relative temperature, times e to the KT. Relative temperature is 70 when T equals 2. And it equals 45 when T equals 5. We can then write out a system of equations. So using this model, we have 70 for t relative when t equals 2. So we get (70 equals t naught relative times e to the 2k. Because again, if t is equal to 2, you get 2k, and t rel is 70. And also, when t is 5, you get 5k here, and t rel is 45, so you have 45 here. Now we can easily solve to find the values of t0 rel and k. Now I wrote this t0 rel pretty badly, so I'm going to try to write it a little better here, just so we can tell that we have the same symbol here that we have here. Okay. There's ways to solve this system. We could say t0 rel is then 70 divided by e to the 2k, and then we could plug that expression in for t0 rel. Okay? That's pretty straightforward. It's going to give us the same thing we get if we do what I'm going to do. Notice if we divide this equation by this equation, that means we divide the left-hand side by the left-hand side and the right-hand side by the right-hand side. If we divide this expression by this expression, t0 rel disappears. Okay, well, it divides out and gives us 1, which means we don't have to write it there anymore. So I'm going to do it that way. So I'm going to say and I'm not going to say that's equal. This divided by this, it means I'm going to divide this by this. So I have the right-hand side divided by the right-hand side, and that has to equal the left-hand side divided by the left-hand side. Now I've switched sides on you, just because the variable I'm looking for, k, we usually want to have that in the left. It's just convention. Okay? It works if we keep it on the right. It's not a big deal, but we're going to keep it on the left. Well, if I divide this by this, and I'm going to do it a little bit carefully, it's pretty clear that the t0 rel divides out, and we're just left with e to the 2k over e to the 5k. And that equals 70 over 45, which is 14 over 9, just simplifying the fraction a little bit. Okay? Well, e to the 2k divided by e to the 5k is e to the negative 3k. And now we have an exponential equation. Our variable is up here in the exponent, so we're going to change to logarithmic form. And we're going to get negative 3k equals the natural log of 14/9. so that k is negative 1/3 times the natural log of 14/9. Now, natural log of 14/9 is about 1.55, so let's just say about 1.6. And I'm going to try to make an estimate here. If that's 2, natural log is 0.7. Visualizing the curve, there's 1, there's 0.7. We've got to come back to there. Okay, well, the square root of e is about, I'm going to say that's about okay, I'm going to guess negative 0.17 when we get done with the arithmetic. Punch that in your calculator. I think you're going to get something that's reasonably close to negative 0.17, 0.16, 0.18, even 0.15, 0.19, but we'll use that as an example. Okay? Sometimes my estimates are pretty good, and sometimes they're totally bizarre. But that seems about right without thinking about it too much. Okay, so here we have our value of k. Now what do? Write that out here. And we're going to plug that into either this equation or this equation. Whichever one we do, our exponential is then going to have some numerical result. And then we just have a number here, and we can solve for T0 relative. Okay, so okay, 70 equals T0 relative e to the 2 times negative 0.17. And I don't want to do, I need to go 3 terms on the Taylor expansion to do this, and I'd get messed up with my zeros and stuff. So I'm not going to try to estimate it that way. I'm just going to say, okay, e to the 0 is 1, e to the 1 is about 2.7. And if we go a third of the way along that curve, I'm going to guess in other ways that's a third root, so 1.3, 1.69. That seems too high. I don't think this number is very accurate. It violates my mental picture of the curve, but yeah, okay, not that much curvature. So I'm going to say it's about 1.3. Because when I do it with numbers, it comes out between 1.3 and 1.4. 1.4 is too high. It's a little more than 1/3. It's too high, but it's not that too high. So I'm going to say it's probably close to 1.4. Okay, so then, also it turns out that that's real convenient. T0 relative is 70 over 1.4, which is about 50. So that came out pretty conveniently. And that's totally ridiculous. Oh boy, I have a negative exponent there. So, let's just fix that. Just got to fix this number, and this number. But I'm going to get something that actually makes sense, because that made no sense I got T naught relative as like 50, but if I put 50 in here with a negative K, I can't get 70 there, okay? The maximum number I could get for positive T would be 50. And I ignored my negative sign, so this should have been 0.7, this should be 0.7, and magically we get 100 here. And I actually think that's not too far from what you'd probably get. It's probably not going to differ from 100 by too much, but there are a number of approximations in here, so, you know, could be. Okay, so anyhow, there we have it. So now our model is T relative is 100 e to the negative 0.17 t. Now that all came out so nice you'd think maybe I fudged it, but I didn't. I probably wasn't all that accurate, but it wasn't fudging. Just happened to come out really nicely. So, what were our original questions? When is the temperature going to be 100? And when is, or what was the original temperature? Well, originally T was 0 when we took the thing out of the microwave. So that's real easy to evaluate. T relative is 100. So the temperature would have been 170 degrees. Because, of course, T relative is our temperature relative to 70 degrees. If our temperature is 100 degrees relative to 70 degrees, that means it's 70 degrees more than 100 degrees, or 170. Now our temperature is 100. When our relative temperature equals 30, which is 100 minus 70. Remember, how far are we from room temperature? At 100 degrees, we're 30 degrees above room temperature. So T equals 100 when our relative temperature is 100, and our relative temperature is 30. Relative temperature is 100 e to the negative 0.17 t. So 30 equals 100 times e to the negative 0.17 t. Write that again. And now we just use the skills that we've developed in the first several sections of the chapter. And we divide both sides by 100. We see e to the negative 0.17 t equals 30 divided by 100 is 0.3. And something about that makes me uncomfortable, but it's okay. So that negative 0.17 t equals the natural log of 0.3. Now, just showing you how I do my estimates, I just visualize a natural log, maybe here, and when we get 1 when This is E. So we get 0.3 about here. If that's 1 and that's 2.7, then that's about 0.3. That's a natural log of 0.3. 0.3 is over here. Here's 1/2. Looking at this thing wrong. This is down here, and I can't estimate that well. So anyhow, we'll say t equals natural log of 0.3 over negative 0.17. Got to have a better way to estimate the natural log of 0.3. Natural log of 1/2 is negative 1. Natural log of 1/4 is negative 2. So I'm going to say that that's approximately t equals about 9. That would be after 9 minutes. Now I'm just estimating that, and it's a pretty rough estimate. I was a little dumb in the way I started the estimate. I didn't really use the curve. Just using some obvious. And it, oh, okay, wait a minute. Whoa. It's not a base 2 log. This is a base E log. So it's going to get down to that a lot quicker. So I'm just going to say maybe it's 1.3 over the 0.17, and that would be 7. 7.6, and if that's even remotely accurate, I'll be shocked. But nevertheless, take your calculator.
I did calculations with a calculator,
Yeah.
and I came with a number of 8.1 minutes.
Well, 8.1 isn't, 7.6 isn't bad if it's really 8.1. I won't say that I'm going to write home with a great deal of pride over that, but it wasn't too bad. And I have no pride anyway, so it doesn't matter. Okay?
Yeah.
So, that's the process. Now that's 3 examples that we worked out in some detail. The other examples are very similar. There are a couple of questions at the end, but this is not due for a week. We're going to have another class before this is even due. Okay? If you're inclined to work ahead, and there's no reason you should have to because you're doing extremely well, and you have plenty of time, and we're on schedule to finish up the course in kind of a relaxed fashion, okay, without having to press near the final exam. So there's no reason you should work ahead, but if you want to work a couple of these while it's still fresh in your mind, I know, it's okay. It's okay. I know you're going to do well whenever you do it. So you work it out, and there's a good head start for you, okay?
All right, sounds good.
Okay, good.